Hello, welcome to the tutorial for Ridesharing catered towards high school students. The purpose of this tutorial is to introduce students into the concepts of ridesharing. This is our research team, and it consists of De'Von, Monair, and Dr. Joe. We will start with the introduction of ridesharing, then move on to transportation networks, and then move to space, state, time networks with showing how to draw the diagrams, and finally introduce next to nodal modeling. As we go along this tutorial, I want you to keep in mind these 5 questions, which should be answered by the time I'm finished with this presentation. What is ride sharing and why is it becoming so popular? What is a transportation network and how is it related to ride sharing? How do we stimulate the vehicles and passengers on the network? How can software be used to automate the simulation process? And why is it important to me? What is ride sharing? So with ride sharing, instead of using your personal vehicle, you can call or bid for a ride a few minutes before you leave your origin. Or you can pre-schedule a car a day prior. Apps like Uber and Lyft uses bidding systems to pick their customers up depending on the demand and supply of the drivers in your area. On-demand ride sharing allows for the on-demand pickup like Uber and Lyft from using a mobile interface. Prearranged pickups and delivery is usually when a group of people set up a preset pickup and destination, usually like an airport express shuttle. Ride sharing. Why has it become so popular? How do you travel? Is it by bus, train, car, or walk? 91% of households in the U.S. owns a vehicle. And 81% of Americans live in urban settings in 2016 versus 75% did in 1990. And which means there's an increasing urbanization that is happening, which is causing a huge demand on the roads, which equals traffic congestion, and which is why there are trains, urban trains now in most cities to help alleviate the traffic. 1 billion vehicles are in use in the world today. 2 billion estimated by 2035. With this dramatic increase in vehicles in the future, there will be issues that arise like increased carbon emissions. Gas prices will change dramatically. There are a limited supply of roadways that are built depending on the space available and the area and the amount of money available to build a road. Urban areas look for alternative ways for traveling rather than just taking single trips. Passenger trains are becoming more popular to use because they have their own right of way. Also, ride sharing is a growing popular way to travel around. So with ride sharing, instead of using your personal vehicle, you can call or bid for a ride a few minutes before you leave your origin. Or you could pre-schedule a car a day prior. Apps like Uber and Lyft uses bidding systems to pick up their customers depending on the demand and supply of the drivers in your area. For example, if you go to a college football game at ASU and use Uber to pick you up after the game is over, when everybody is trying to leave the stadium and go home, the price of the ride will increase because there is a higher demand for drivers than there are drivers available in that area. Some benefits of ride sharing is that it will reduce driver stress and driving costs, improve mobility for non-drivers, increasing safety and fuel efficiency, and decreasing road congestion and overall societal energy use and pollutions. Ride sharing can be used by anyone who desires to use it. Even high schoolers can use it to take them to sport practice or to the mall. It's really simple to use, and most of you guys probably have used it at least once by now. You can see the car or vehicles going from the depot to pick up 3 passengers and drop them off at 3 different destinations. Like passenger 1's at work, passenger 2's at school, and passenger 3's at the store. And typically this is how ride sharing works. Someone usually requests through a platform, requests a service from the platform like a mobile app. Then the request is sent to Cloud Computing Center for pricing and congestion credit. Then the request is sent to a regional traffic management center for a vehicle to be sent to the requester. And as the vehicle arrives for pickup and delivers the passenger. Then it kind of depends, the way the order the passengers are dropped off is depending on whose destination is closer. So it doesn't matter what order you picked up in. Usually the vehicle goes the most optimum route. So whatever route is the shortest route to pick up, service all these passengers. What are transportation networks? Node is a point which lines or pathways intersect or branch. Traffic modeling is used as intersections, interchanges, and highway ramps. Then link connects two nodes together. In traffic modeling, it is used as road segments in between nodes. And nodes and links are used for 6-node transportation networks, which a transportation network models the traffic flow in a specific area. Transportation network. How do we model? Vehicle routing problems with pickup and delivery with time window, or ride sharing problems modeled by optimization problems. There's the number of passengers needed to be transported in a certain time frame, and there are specific pickup and delivery time windows that are occurring, need to be met. And the goal is to find the optimal route for a fleet of vehicles to visit the pickup and drop off locations to satisfy the requirements. And you can see there's Super Shuttle, Ruby Ride, Zipcar. These are examples of a few companies that use this method. Here is an example of VRP with time windows. They are used for food delivery, used for residential transportation, home to hospital, used for package delivery, UPS, Ruby Ride, Vons. These are examples of companies that do time windows. Here's an example of a vehicle routing problem, aka VRP. It is a combinational optimization and integer program problem which asks, what is the optimal set of routes for a fleet of vehicles to traverse in order to deliver to a given set of customers? It's generally known as the well-known traveling salesman problem, which the salesman goes around delivering and dropping off items. The VRP concerns the service of a delivery company. How are things delivered from one or more depots, which has given some of the set of home vehicles and operated by a set of drivers who can move on a given road network to set a set of customers. It asks for a determination of a set route, such that all customers' requirements and optimal constraints are satisfied, and the global transportation cost is minimized. The cost could be money or distance or time, whatever you want. But pretty much the VRP will tell the service vehicle what route to take to satisfy the requester's desires. And the goal is just to find the optimal route. As you can see with this example, here's a vehicle picking up one passenger, dropping them off, picking up another, dropping them off, going back to depot. And prices are reasonably set. They're usually they're not too too cheap, but not expensive. So that's where the supply and demand comes in effect with the pricing with these. Here's another vehicle going. It's actually picking up 2 passengers first, then it's delivering them, then it's going back to. Then this one's picking up 2 passengers and delivering them, then going back to the depot. Here is an example of VRP. The VRP concerns the service of a delivery company. How things are delivered from one or more depots without giving a certain route
home vehicles and operated by a set of drivers who can move on a given road network to a set of customers. It asks for a determination of a set of routes such that all customers' requirements and operational constraints are satisfied and the global transportation cost is minimized. Like ordering packages online, and they will tell you, like things like this. It's like when you order something off of Amazon, they tell you that they'll arrive so that at some point in that day before 8 p.m. You don't know, you have no idea really what time it's gonna come, but it's just before 8 p.m. or at the end of the day. And this, you can see, it's just kind of just like loose time windows with this. It's virtually none. And you can see this example, the truck is picking up packages or delivering packages. Then he's delivering food. I'm going back to the depot. Now he's picking up packages and going back to the depot. This is exactly how VRPs operate. In this example, I'm showing how the vehicle will travel along the 6-node traffic network. Vehicle 1 picked up passenger 1, and vehicle 2 is servicing passenger 2. So they both start at the origin, but vehicle 2 leaves 10 minutes later because the time window for passenger 2 is later than the time window for passenger 1 for pickup. So then both vehicles travel the same path. So they started at the origin, and 1 equals 10 minutes and 2 equals 20 minutes. So it traveled from the origin to node 4, which is 10 minutes. And from node 4 to node 2, which is 20 minutes. And from node 2 to the pickup node, which is another 10 minutes. So it takes 40 minutes for both vehicles to service this passenger. Then it goes from node, after they pick them up, then it drops them off. It goes from node 2 to node 5 to node 6 to node 3 and delivers them. Then it goes back to the depot at node 1. Then it's finished, the job complete. But to keep it simple, I showed you an example. You can see the numbers 1, 2, 1. This is showing you the example from the vehicles traveling from the origin to the service to pick up passengers. Then you guys can calculate the rest of the vehicles going from the pickup node to the delivery node through the routes I just mentioned, and from the vehicle going from the delivery node to the depot, which you can all calculate. So this is an 8-node transportation network, nodal system. Nodal networks can be extremely large, like in urban areas, which makes it more complicated to analyze by hand. In this example, I want to illustrate how you would need to travel from node 1 to 4, and there's multiple routes that can be taken to travel from node 1 to 4. However, traveling from node 1 to 5 to 6 to 4 is the shortest path. You see the cop car is going in the fastest way to node 4, and the red car is going the slowest way. But there's all these possibilities of getting to node 4 from node 1, you can see. But the cop car is node from 1, 5, 6 to 4 is the shortest path. Now here's a more complicated 8-node network. And as the nodal networks grow larger, the complexity of analyzing the nodal networks become difficult. This Nexta is an open source software that analyzes traffic in large nodal networks, because you wouldn't want to try to solve this by hand, because it's huge. Like, it would be a nightmare. This is a nodal network of the Phoenix metropolitan area. You can see the complexity of the nodal networks in the urban areas. It's huge.
How can software be used to automate the simulation process? Nexta stands for Network Explorer for Traffic Analysis. It is an open source graphical user interface GUI, and it analyzes traffic assignments and simulations of data sets. It can be used to represent 6-node networks. It tells the traffic speed, density, queue, bottlenecks of large-scale networks. They have built-in interfaces with Google Earth and GIS files. The inputs agents go into the system to tell the nodes that the vehicles need where the vehicles need to be traveling on, and it gives the location of the path nodes. The output agents are used for the output of the path, and these sequences tell the vehicles the way which they will travel. Also, the path time sequence the vehicle will have to follow to make sure they can pick up the passengers on time. And there's free software where you can go to this link below and download Nexta and learn how to use it. And there's a learning step-by-step tutorial at learning this link below. So this is a nodal network of the Phoenix metropolitan area. Phoenix metropolitan network has over 40,000 nodes and links in the network, and we use a software called Nexta to model it. Nexta has the ability to show the density, volume, speed, queue, impact, bottleneck, emissions, and so on, more traffic analysis tools. As you can see, as networks in urban areas are very complex. Transportation networks. How do we model? VRPP-DTWs are modeled in 6-path nodal networks. Remember, VRPP-DTWs have time windows to where they need a certain number of passengers need to be transported in a certain time frame, and these must be satisfied these conditions.
So here's an example. 2 passengers are requesting a ride. Their origins and destinations are different. Also, their time windows are different. Make an acceptable route and time window that the driver can take to satisfy the requester's requirement. The passenger's one preferred window for departure is from 8:10 to 8:17, and passengers 2 is from 8:17 to 8:21. So you can see they're going to ride share because their time windows are pretty close, and they're pretty close to each other. So the vehicle, and this we're counting these as 1 equals 1 minute, 4 equals 4 minutes for this example, the timing. And the vehicle is going to travel to pick up passenger 1 at origin 1, then go pick up passenger 2 and drop them off. And you see it's all within their time window, the delivery time window and pickup time windows are satisfied. So the vehicle completed its job and went back to the to the depot, which is at 8:38, and it served pretty much the time of operation from the vehicles from 8:10 a.m. to 8:38 for these 2 trips, and it satisfied all the requirements. State space shows the vehicle location in respect to time and carrying capacity of the vehicle. Space time graphs show the location of the vehicle in respect to time. Carrying state represents the carrying capacity of the vehicle. And here are some examples of them. These graphs, usually state space is represented in binary. It could be in binary or represented in P1, P2, P3, or depending whatever the capacity is. And these are just graphs to show like possible combinations with like a three passenger carrying state. As you can see, this vehicle picked up 1 passenger or 2, then it dropped them off, and this vehicle is doing the same thing, but it's not ride sharing, it's just picking up 1 person. This one is a shared ride. This one is serving a single passenger at one time. And you can see how the state changes from, it starts in the origin 0, 0, then it picks up a passenger, it gets P1, then it drops off the passenger, then it's 0, 0 again. And same with this one, it goes from 0 to P1, P2, both are passengers are in the vehicle, and you dropped off from passengers, so it's only P2. This is the problem that we will create a state time graph with. And passengers 1 pickup time is from 7 to 7:10. passenger 1 arrival time is 7:10 to 7:15. So you can see the vehicle is going from node 5 to node 6 to node 4 to node 2, just the fastest route to pick up this passenger, then to node 1 to origin, then dropping them off in his area, then going back to the depot. Then you can represent this in a graph. This is a state space-time graph, and it shows the x-axis is the time dimension, and y-axis is the space dimension. And state space-time graph shows the location of the vehicle servicing a passenger during the time window. So the vehicle waited for a minute at the start, then it traveled to node 5, then to node 6, then to node 4, then down to node 2, then went to node 1, then it went to the origin node, the pickup node, which it picked up the passenger in this time frame, the green arrow. Then it went back to node 1, then it went to node 5, then 6, then down to node 4, then it went down to the dummy delivery node. It delivered the passenger in the blue arrow. Then, which as you see is within the time constraint. Then it traveled to node 4, then to node 3, and to the dummy depot, back to the depot. State space networks show the ride-sharing path of the states at different spaces. The vehicle is picking up and dropping off passenger P in different spaces. Figure 4 represents the different carrying states of the two passengers serving across different spaces. The carrying state changes as pick up each passenger from the origin and delivers them at the destination. So you can see the vehicle started at the dummy depot, 0, 0. Nobody's there. The carrying state 0. And now it's P1. Then it's P2, picked up a second passenger. Then dropped off one. Now it's just 1. P2. Then now none. Then the state went back to 0 and he went to the origin, or his dummy depot, and 0 again.
How can I get involved? Study engineering, math, science, computer science, and learn how to analyze computer network from the learning document found at the link below. Studying engineering and math and computer science specifically trains you for a technical background which provides you the math experience to quite to understand how to analyze transportation networks, because the math optimization problems can get really heavy, and it's best to have some type of basic background so you can kind of get a glimpse, and as you go further along in your education degree, you'll start to understand it better. For my closing remarks, I'd like to give you guys a little background on myself. My name is De'Von Jennings. I'm attending my BSc in Civil Engineering class of 2016 from Arizona State University. I'm attending UC Irvine for a PhD program in the School of Engineering, Civil Environmental Engineering department. And I graduated out of Columbus City Schools, Beechcroft High School, back in 2012, and I am a Gates Millennium Scholar, which is from the Bill and Melinda Gates Foundation, in the cohort year of 2012. And also I'm a Children's Defense Fund Beat the Odds Scholar. And I'd like to thank Dr. Joe for giving me the opportunity to perform research under him and help improve my presentation skills and professional skills. And also I'd like to give a large thanks to the University Transportation Center for supporting this learning research project.